Example 36. Suppose that the depth of uniform flow in a 1.22 meter wide rectangular channel is 0.35 meters. Find the change in water surface elevation caused by a 300 mm wide bridge sphere in the middle of the channel. The flow rate is 1.4 cubic meter per second. So let's compute for Q first. 1.4 divided by width 1.22, 1.148. So from here we can compute the normal critical depth, which is cube root of 1.148 square over 9.81. So 0.5122 meters if there are no obstructions like that pier here. Then the depth is 0.35 meters compared to that. So meaning to say at the depth of 0.35, because this is less than the normal critical depth, it means that this occurs at the lower stage, or the flow is supercritical. Then V1 is equal to 1.148 divided by depth 3.427 meters per second. Then the specific energy at section 1 is 3.427 square over 19.62 plus D1 0.335. So 0.9336 meters. If the bridge sphere will cause critical flow, because it is an obstruction, it will cause disturbance, and that disturbance might cause a wavy surface. So we must equate this to 3 halves of the critical depth for rectangular sections. So at critical constriction, because the barrier or the pier will reduce the width. So it is a form of a constriction. So 0.936 equals 3 halves of the critical depth. The critical depth, therefore, when there is a barrier, is 0.6224 meters. Then let's compute for Q critical with the barrier, which is depth sub C critical 0.6224 times critical velocity, which is square root of G d sub C for rectangular sections. So 0.6224 times square root of 9.81 times 0.6224. So the critical flow is 1.538 cubic meter per second per meter. Then this is equal to critical width times Q sub C is equal to 1.4 by continuity. So critical width times Q sub C is supposedly capital Q, and it is equated to original capital Q by continuity. So it is 0.9103 meter, the critical width, and this is less than 1.22 minus 0.3 width of the channel minus the barrier or the bridge pier. So 0.92. They are not equal. If they are equal, then this is the critical width, supposedly. Since they are not equal, then the actual velocity must be computed, which is 1.4 over 0.92, that's small q, divided by depth sub 2. So v sub 2, 1.4 over 0.92. This is v. This is v, velocity through the net width less the barrier, divided by depth 2, so 1.522 over depth 2. Then we equate the specific energy, 0.936, to this velocity head at section 2 less the barrier plus depth sub 2, and this is a cubic polynomial. Therefore, there are 3 roots, so 0.9336 equals 0.1181 over d sub 2 square plus d sub 2. So d sub 2 cube minus 0.9336 d sub 2 square plus 0 d sub 2 plus 0.1181 equals 0. So we obtain three roots using your high-tech calculator. The first root is negative, the second root is 0.6723, and since this depth is greater than 0.6224, that means the flow is subcritical. The next root is 0.5696, which is less than this value, so it means it is supercritical, just like the original. And the third root is absorbed because it is negative. Therefore, since there's no mechanism or it is impossible for a jump to occur, it is just a barrier, so therefore the flow remains supercritical, and this is the value of depth 2 due to the presence of the barrier. Therefore, 0.5696 minus original depth 0.335, that's the expected rise in the water surface due to the presence of that barrier. So water surface rises by 0.2346 meters in the barrier with the presence of that barrier.